The walls, the roof, and the floor in this room is covered with these absorbing wedges, as you can see here. So the purpose of these wedges is to remove all acoustic reflections in this room. So that implies that the acoustic field in this room is very, very special. So for instance, if I move now twice as far from the microphone as I am now, then my voice will sound much, much weaker than before. In fact, the sound pressure is proportional to 1 over the distance squared in a field like this. And why this is, we will talk more about in the coming presentation. Now we're going to talk about spherical acoustic wave equation. And as I mentioned before, the typical applications are outdoor sound propagation or sound propagation in large volumes. And if you remember, we have seen this example before when you have an alarm and want to check how, well, compare the sound pressure close to the alarm and at some distance. So this is a typical application where you can use the three-dimensional linear acoustic wave equation. So in Cartesian coordinates, as you may remember, it's the wave equation looks like this. We have the x, y, z coordinates and the speed of sound c. So in spherical coordinates, that is more suitable for use in outdoor propagation when you have a small source, small size source. And if you transform this, the Cartesian version of the acoustic wave equation to spherical coordinates, r, theta, and phi, the equivalent, well, the wave equation looks like this. So in this case, r here, of course, is the distance from the source in origo here to the observation point. The angle theta here is the angle, in this case, between the z-axis and the vector between the origo and the receiver point here. And phi is the angle between the x-axis and the projection of the vector r on the xy plane, like this. We shall now simplify things here by assuming a spherical symmetric field. And that means that we assume that we have no angle dependence of the sound field. And that means then that these two terms will be zero in a spherical symmetric field with no angle dependence. So the wave equation in this case simplifies to this. So if you remember now the one-dimensional, this is actually a one-dimensional wave equation because it's only dependent on r. But the difference now with the spherical version to the Cartesian version is these two terms here, 1 over r square and r square terms. These are not present in the Cartesian case. And that these two terms, these two factors, I should say, actually cause the spherical wave pattern that we shall see later on. So we are going to investigate the model problem. So we should determine now the sound field around a sphere. Imagine that you have a sphere here with a time-dependent radius a. And when this, and we should also assume that this radius oscillates around an average value with a single frequency oscillation. And that will make it possible to use these complex quantities as we have used before. So assume now also that the boundary, the spherical boundary, the speed, the velocity of a point on the boundary is denoted v. And it's also time dependent, of course. And in an observation point, a certain distance r from the center of the sphere is denoted p. So that is a sound pressure then in the observation point. So as I said before, we are going to use complex sound pressure, complex quantities. So we assume now that the sound pressure field, the complex sound pressure field, can be expressed like this. We have a distance dependence sound pressure amplitude, and this complex exponential frequency dependence e raised to I omega t. So insert this into this wave equation that we saw before. And then if we perform the time derivation, then you know that we have a double multiplication with I omega instead of the second order time derivative. And we can also perform this derivation with respect to the distance r. Then it turns out that after the time derivation, we end up with this differential equation. And this the differential equation has solutions. We can express, two independent solutions, which we can express like this. So this a plus here and a minus here are unknown constants. And then you have this complex exponential dependence on the distance from the source here, also in the exponents of these two terms here, these two factors here. So this first term here represents an outward propagating wave. So this is a spherical symmetric wave propagating out from the source, whereas this one, when you have positive sign here in the exponent here, represents an inward wave. So this is a wave coming out from outside and going into the source, as if you have a sink, a sound sink instead of a source in the spherical center. So that means that in our case, we can, since we are interested in, in the source, sound radiation from a source, we can neglect this part. This is of no interest to us. So we only consider this first part, the first term. So that is our solution, describing the sphere's sound radiation. So what remains now is to determine this A plus coefficient, this unknown coefficient, and that we can do from the boundary conditions at the sphere surface. Because the sphere boundary velocity must somehow be coupled to the particle velocity of the air or the medium just outside the sphere. So that is expressed as a boundary condition at the sphere surface. So UR here is the radial component of the particle velocity. And if we go close, have an observation point very, very close to the sphere surface here, then it's obvious that from physical reasons, the particle velocity in the immediate neighborhood of the sphere surface must be equal to the sphere's surface velocity. So this equation here, this boundary condition must be satisfied from physical reasons. So the particle velocity, the radial component of it, evaluated at the sphere surface, must be equal to the sphere's surface velocity, v. And in order to determine this unknown coefficient a plus, then we must have a connection between the sound pressure and the particle velocity. And that is given by the equation of motion expressed in spherical coordinates. And this version then is spherical symmetric coordinates because we have no angular dependence here, as you can see. So if we introduce then the sound pressure, complex sound pressure field, as we have determined before when we solved the differential equation, perform the, integrate with respect to time, that this integration, time integration, causes this division with I omega. And then if we derive, take the derivative, partial derivative with respect to r, then we obtain this expression for the particle velocity as a function of the distance r and time t. And as you can see here we have the unknown coefficient a plus. And now we can insert this into the boundary condition. So we can replace r here with a0, the radius of the sphere, and set this equal to v, the known velocity of at the sphere surface. So when we do this, we can determine this a0, this a plus, and introduce it in the complex sound pressure expression. And then we end up with this expression for the complex sound pressure at distance r from the sphere center. So this is the sound pressure field around the sphere, the spheric symmetric sound pressure field. And as you can see here, what is interesting here that we saw in this first video, part of the video, is that the sound pressure amplitude is inversely proportional to the distance between the source center and the observation point. So it's 1 over r. So if we double the distance between the source and the observer, the sound pressure amplitude will be halved. So that means actually 6 dB sound pressure level reduction if we double the distance. Okay, and the same goes for the particle velocity. So if we insert this a plus coefficient, then we find this expression for the particle velocity as function of distance r from the source center. Here is an animation, and as you can see here, each dot here represents a volume element, a medium element. And as you can see, very, very close to the source center here, the oscillation amplitude of the air particles is very large, and the amplitude is reduced the further away you go from the source center. Now, as you know from before, we can introduce specific acoustic impedance as the ratio of the sound pressure and the particle velocity. And if you remember, for the plane wave, this ratio was rho c, the density times the sound speed. And for a spherical wave, this expression will be this. As you can see here we have rho c, exactly as for the plane wave, but then we have a factor here that depends on the distance and the wave number. Actually, the wave number k times the distance. And as you can see here, since we also have this imaginary unit here, this is a complex valued factor. And this is of great importance from the spherical wave characteristics compared to a plane wave characteristics. So we will use it a lot later on in the course. And as I mentioned before, this specific acoustic impedance, it's very valuable if you know one of the fields, either the sound pressure field or the particle velocity field. Then you can calculate the other field simply by multiplying or dividing with the specific acoustic impedance. Okay, now we should specialize this. What happens if the radius here, A0, becomes small, acoustically small, that is small compared to an acoustic wavelength? What happens then? Well, as you can see here, if R here is equal to A0, then you can simplify this impedance here, and that is what we are going to do. So if the source becomes acoustically small, the radius becomes small compared to the acoustic wavelength. That means then that the wave number times the typical radius of the source must be significantly smaller than 1. So that means that this term in the denominator here can be neglected compared to the 1 here. So that means that the sound pressure field then becomes approximately equal to this. So this IK here, that is what remains, the sound pressure field becomes approximately equal to this expression if we can neglect this Ka0 compared to 1 in the specific acoustic impedance. Then we can introduce something that we call the acoustic volume flow, Q. Now that is equal, if you see the units here, it's equal to the surface area, S, times the velocity, vibration velocity of the surface. And in this case, we have a surface area here. See, this is equal to the spherical surface area. And here we have the velocity, vibrating velocity of this spherical surface. So this factor here we can replace with the acoustic volume flow of the sphere, Q. And if we include this EI omega t, then we have the complex acoustic volume flow equal to this expression here. So the resulting complex sound pressure field can be expressed in terms of the acoustic volume flow, like this expression. And this is in fact what is better known as an acoustic monopole. And acoustic monopoles are very, very useful sound radiation model for small sources, small acoustic sources. If you have, for instance, exhaust from a car engine, the exhaust gases, if the exhaust pipe has a small diameter, small radius, then you can use the acoustic monopole model to describe and calculate the sound radiated from the exhaust. So there are lots of uses in practice for acoustic monopoles. There are many important engineering sources that can be considered as acoustically small. And if this is the case, you should always check this condition that K times the typical radius of the source. Then you can use this monopole model. And that was all for now.